We have a laser pointer here, which you can use as far as your overheads are concerned up there. You have a couple of ways of going ahead and getting these things changed if you want to. The route I'd recommend, how many slides do you have?
Probably 20.
Okay, just to go ahead and take care of these yourself if you want to down here.
That's fine.
There's a walk-around microphone. Yeah, there's a walk-around microphone up here. I guess I recommend you use. It gives you a little more mobility.
Okay.
And as far as your view grants are concerned, okay, there are the two view grants and works. I'll give you the slide first. Do you remember who you gave it to?
Bob's right here.
Bob. Okay.
Bob, can you check the front? Do you have some slides or anything?
Let me strap you up with this.
Do you know where they are? I need to take them upstairs.
We do have the laser pointer. That should work out just fine. You can see the beam that it projects.
Yeah.
We have some water down here for you.
Okay.
There's a standby laser pointer system up here, which we can turn on and use in case the batteries in this thing goes out.
Do I turn the lights off myself?
No,
Don't
don't worry
take care of
about
the
any of that. The only thing this controls is the lights here on the podium itself.
Okay.
Otherwise, everything is under control, and I think we'll be okay. I'll be sitting down right down here. If there's anything you need in terms of volume or anything like that, let me know. Thank you.
I believe it's about time to begin. It's my pleasure to welcome Professor B. Stanley Pons from the University of Utah, a person who has rapidly become a household word and I think has created a stir in the scientific community like I have never seen before. I think that's evidenced by the fact that we have once again been able to fill this auditorium for a colloquium. Although Professor Pons is well known, perhaps some of his background is not, and I'd like to take just a couple of minutes to brief you on that. He graduated from Wake Forest University in North Carolina in 1965 with his bachelor's degree. He continued his education at the University of Michigan, but after 2 years interrupted it to work in a family business for a period of about 8 years. Returning to his education in 1976, he worked with Professor Fleischmann at the University of Southampton in England, where he received his PhD in 1978. He joined the chemistry department at Oakland University at that time. Subsequently, after a 2-year period, he went to the University of Alberta. And in 1983, he joined the chemistry department at the University of Utah. In 1988, he became chairman of that department. With pleasure, I want to welcome him here.
Thanks very much for this very kind introduction. Before I left yesterday, the dean of my college said that he remains amazed at what it takes, what an electrochemist has to do today to get an invitation to Los Alamos. So he said, you still know how to attract attention, he said. So, but thank you very much for the invitation to come down. A little bit of a history. Professor Fleischman, who was at Southampton when I got my PhD with Alan Buick, told us of some results he had seen in for separation factors of deuterium and hydrogen in metal lattices, particularly in palladium. And those results seemed very strange to a number of people for some time. In Utah, some 10 years or 8 years later, so we were collaborating on other things. And in the context of trying to make metallic hydrogen, that was something that I had been interested in for some time, trying to look for ways to do that. We discussed the possibility of doing this in metal lattices because of the very large high pressures or high apparent pressures that you could derive in these metal lattices. So these alternate methods of gaining high compression or high pressures in lattices then led to a simple calculation, and that if you considered the raising of the chemical potential of a substance inside a metal lattice just on the basis of the potential difference that you measure in certain metal lattices, if you take that calculation, it showed that you could indeed achieve astronomically high pressures if you were to try to do it by hydrostatic means. It's the same sort of situation that one has to consider when you consider how do you prepare sodium and chlorine gas from its from ordinary salt? How do you change this into its elements if you don't use electrochemistry? Well, electrochemistry in electrochemistry is trivial. You take the molten salt and you use platinum electrodes, and you can certainly derive sodium and chlorine. To do that by any other process, by any other physical or chemical process, is extremely difficult. You could not do it to any significant extent. So the point here is that the lesson we learn is that the energy in some electrochemical experiments, you put the energy where the energy is needed. So anyway, these sorts of pressure equivalents that we were calculating immediately led to the thought that there must be more interesting reactions that we could look at other than metallic hydrogen. And indeed, we considered the possibility of fusion of like nuclei in these metal lattices, specifically deuterons. So we designed a rather far-fetched experiment, and that was hanging a cube of palladium into a large volume of D2O electrolyte for some months. We got a negative result. We then made some modifications to the electrode. We changed the current density sharply, and a few hours later, we discovered that the cube had vaporized most of the equipment around it. So let me show, so from then on we decided to change the experiment, which we did. We started over at a very low level, and for the next 5 years tried to be a little bit more careful. And the reaction then which we're considering, if I could have the first slide. Okay, the cell that we're talking about is this. Is it properly focused? There you go. Probably change it here. The cell is a palladium rod, which is the center portion here, which is immersed in a D2O lithium deuteroxide electrolyte. We have a temperature measuring device inside. This is a calibrated thermistor. You have a tube for injecting and replacing the D2O that is electrolyzed out. You have a simple resistance heater so that we can do Newton's law of cooling curves or the heating coefficient measurements by injecting a known current and a known voltage into this device. And we have a secondary electrode, auxiliary electrode, which are these horizontal lines, which is platinum wire wrapped around a glass basket, which totally surrounds the electrode. You then have a cell. The external portion of the cell, which is all glass, can either be an evacuated dewar if you're looking for very small heat changes. An evacuated dewar is best if you're looking at medium heat changes on the order of a tenth of a degree or a degree. Then you can just use a cell that's not evacuated. And if you're looking at very high temperatures on some of the larger electrodes, then we would just use a single wall cell in order to increase the heat flux through the device so we can make a more rapid measurement. And let's see, the whole thing is mounted in a KLF plug at the top. All that's sealed with parafilm, so there's only one avenue of escape for gas, and that's through this fill tube. And all of this is mounted in another KLF tube in the bottom of the cell. So it's quite a simple cell. This is the Utah U1 tokamak. We couldn't use the cooling baths you have here, so we used a Rubbermaid. It was considerably cheaper in those days. But in any case, this is a photograph of the cell, and the main power connection is from a potentiostat then that goes into to the anode and cathode, and that is mounted externally into a fairly large, highly temperature bath that has temperature that's controlled to within 1/100th of a degree. And then the thermal measurements are measured like this. Radiation measurements are made by putting this cell into an appropriate spectrometer or device, or withdrawing material from similar cells and injecting them, the samples into other spectrometers, scintillation counters, and things like that. Well, the reaction we discuss here is the reaction of the generation of deuterium by electrochemical reduction at the palladium electrode. The first reaction is generally accepted to be the first step in the actual mechanism, and that is the adsorption of D atoms on the surface of a metal. This is the same mechanism that you would see at a platinum electrode or any noble, or at electrodes where you have adsorption of hydrogen. You then have diffusion, not migration, but diffusion of the adsorbed atoms into the lattice. This is the strange phenomenon which separates palladium and some other metals from all the others. And then you have any number of competing reactions. This reaction is thought to be the mechanistic step in our system. There are certain other recombination reactions that might be considered. So the overall reaction, or the overall chemical potential of deuterium in the lattice, must be determined by the relative rates of these two, of the first and the third reaction. So the overall reaction path for D2 generation, the relative rates of that generation then will determine the activity of the deuterium in the lattice. In these experiments, at any voltage less than about 50 millivolts positive to the reversible hydrogen potential, we will have that the lattice is in the beta palladium hydride form, or beta palladium deuteride in our case. The deuterium is in the lattice as deuterons, D+, and the diffusion coefficient, at least in the alpha phase, has been taken to be 10 to the minus 7 square centimeters per second. That's the given value at 300 K in the alpha phase. So upon adsorption then, it is well known that the atoms then diffuse into the metal lattice, but not as atoms, but as deuterons. So if we can draw a potential energy surface here for the dissociation of water into adsorbed palladium atoms. We see then that these atoms on the surface then diffuse into the metal lattice and will do so at the diffusion coefficient then I just mentioned. If we then, an electrochemist then would consider or would view the situation that the potential energy surface now in this strong potential field of 10 to the 11th volts per meter near the surface, or approximately that near the surface, we have a shifting of the potential energy surface down, and it's by an amount that is the difference between the solution potential and the inner potential, or the galvanic potential in the metal. So now the deadsorbed diffuses into the lattice into a very shallow potential well. I'll mention more about that in just a moment. And the electron enters the band structure of the metal, and we know that because in migration experiments, if you now put a potential field across this electrode in solution, you can draw the deuterons to one side of the electrode or other. This is quite a well-known phenomenon. So it is in the lattice as D+. In other words, we have a low temperature plasma at this point. If we look at the thermodynamics, which I wish I had not done that yet, here we go. If we look at the thermodynamics of this situation, It's also well known that the electrochemical potential must be the same across the interface, and therefore the sum of the chemical potential in the Faraday times the solution potential must equal the chemical potential in the lattice times the Faraday times the inner or galvanic potential in the metal. And so we can measure this quantity by a number of electrochemical means, and the minimum value which you measure is on the order of 800 millivolts. So we say, wonderful, so what? That's not a big deal. But the big deal is that if you were to try to change the chemical potential of deuterium gas from this process by compression, by hydrostatic compression of deuterium, then you would indeed have to develop 10 to the 27th atmosphere. So this is the astronomical pressures or compressions that we thought that we would have available to us for consideration of a reaction. The point is although these pressures are not attained, the cohesive strength of the palladium lattice, I think, is only about 4,000 atmospheres. The process of dissolution of deuterium into that lattice is a very high energy process. We also point out that deuterium gas is never seen in the lattice. There's very little, which indicates that there's very little s electron character surrounding the deuterons, and indeed the electrons, the deuterons are shielded then by the electrons in the lattice, and it is indeed D plus in the lattice, as I mentioned. Further, the observation of these very high constant separation factors, if you measure the separation factor for hydrogen and deuterium in the metal lattice, you find that they go to extremely high values of about 9.5. If you measured in solution, just from the electrolysis of hydrogen and deuterium in the solution at all mixtures, you come up with a value that's easily predicted by statistical mechanical theory. And that's what, 1 over 2, 1 divided by 2 raised to the 3/2 power, and that's exactly what you observe. So the only theory that explains the very high pressures or the very high separation and constant separation factors that you see in the lattice as a function of applied electrode potential indicates, or it can only be explained if the hydrogen and deuterium in the lattice, the hydrogen in the lattice is considered to be a classical oscillator. In other words, a zero point energy, not as a quantum oscillator. So in this situation, we have the possibility, or we have high compression, we have extremely high mobility. These things are very free to move in the lattice. We therefore have many collisions and very long confinement times. So we therefore considered the possibility under these high energy conditions reactions of this other form, reactions of this form. I don't know how that got in there. Let me. I've missed a slide somewhere. That was it. So we considered reactions of this form then in the lattice. And our own evidence for these reactions occurring are that we have measured a neutron flux under certain circumstances. We have measured the mass spectroscopy of the products, which initially were quite ambiguous, but more recently we've obtained some interesting results, which I'll mention in a few minutes. We were really looking for helium-3, which is extremely difficult with the equipment that we had or have to work with. We've measured the gamma ray spectrum associated with a thermal neutron gamma reaction with the water in the water bath, tritium measurements, and calorimetric measurements. So I'd just like to take a minute or two to discuss each one of those results. I'm sorry that one slide was out of order. The one way to measure tritium, of course, would be to use a sealed cell. This might be a nickel cell, and to catalytically reconvert the deuterium and oxygen by some catalytic converter in the top. Dr. Gottesfeld here has given me some very good hints on how to do that, and look for the tritium the TDO or T2O accumulation in the liquid state. We did not do that. We just let the system run and counted on the fact that some of the tritium atoms in the lattice, which would be exchanging with deuterium on the surface if formed, then would indeed give rise to exchange with the water and an accumulation of tritium in the water. So this is a scintillation spectrum of the or the beta ray spectrum of the solution, which grows in time, is predicted by solving a differential equation which takes into consideration the accumulation as a function of the initial tritium concentration, the sampling frequency. You'll be withdrawing samples, and so you have to take that frequency of sampling into consideration. The total number of atoms of deuterium in the cell to begin with, the DT separation factor, the rate of the nuclear reaction, and of course the rate of electrolysis. And you get a curve then, and from that curve you can determine the predict the rate of accumulation, which fits very nicely to the observed result. Further, we use a sodium iodide detector to look at the gamma ray spectrum at approximately the Fermi distance from the cell as the neutrons pass through water. And we have indeed obtained a spectrum which has a peak near 2200 keV, which we attribute to the in-gamma reaction of thermal neutrons with water in the solution. And further, with a Bonner sphere of not very high sensitivity, we detected in these particular experiments a direct neutron flux of thermalized neutrons. The calorimetric data, I'll give you some results and then show you exactly how these were obtained, were made on a variety of electrodes. These excess heats, I will show you how these were calculated in just a moment, but these are excess heats that we measure, and we express them as specific excess heats, watts per cubic centimeter, as a function of current density, 864 and 512 for these various size rods. We went to rods because we wanted to show that the reaction, or that the heat that we were observing, was a function of the volume of the electrode and not a function of the surface area, which I think it clearly shows. This is a sheet electrode which we used some longer time ago. It's not the best configuration in the world, and the cube is the one that I referred to earlier about when we made a switch from 250 milliamps per square centimeter after running for 9 or 10 months to 125. Something happened in the cell. A highly exothermic reaction occurred in the cell. We've also now noticed highly exothermic reactions on these electrodes, on 4.4 by 10 centimeter electrodes after running for some 800 hours. Again, we're seeing very large bursts of exothermic energy there. The curves were measured in the simplest possible way. The excess heat is measured fairly in this manner. We will notice that after we start our measurements at somewhere on a typical measurement, we would start at, say, 200 hours. We would then inject heat into the system by applying a known amount of energy into a resistive heater. We then let the system come to equilibrium. First of all, we top the cell up the night before, 12 hours before, so that the cell is totally filled with the D2O because it's been electrolyzed out, and the thing is left for 12 hours to equilibrate. Then first at 6 in the morning, typically we would start making measurements for 3 hours, and then temperature measurements for 3 hours every 10 minutes. And then then the heat would be applied. You wait till it comes to equilibrium again, and then you turn it off, and from that you can calculate the heat transfer coefficient. If you know what the amount of heat that you're putting in, you know the delta T that caused before it got back to equilibrium, then you can easily calculate the rate of the loss of heat to the surrounding solution. You then know the potential at this particular point. You know what the constant current is. You know what the temperature difference is between the cell and the water bath, so the excess temperature in this case would be 6.86 degrees, and from that then you calculate the excess heat. And that's demonstrated on this slide. This particular value is fairly new, and it's not in this table, in the table you saw just a moment ago, but this is just a typical calculation. So you know what the energy input into the resistive heater is. If you divide that by that delta T, that gives you the rate at which the heat is being dissipated to the solution. You know the heat output from the cell is also this cooling constant times the temperature difference, so you know what the output heat is. You calculate the joule heat, you know the cell voltage, the cell current, the thermoneutral potential for the reaction in the cell, and from that you can calculate the excess heating. We have also published a table of break-even, and this is based, when you want to talk about break-even, you of course have to take the various reactions in the cell into account. And in this particular case, we've considered 3 cases, and that is this reaction based on the joule heat supplied to the cell and this anode reaction. So that's what you see in the starred columns. The double star columns take the percent based on the total energy supplied to the cell, and the third one is the percent break even based on an ideal reaction. Now this reaction may be this is a theoretical reaction, but it's a well-known reaction in electrochemistry, and that reaction is simply that you collect the gas, the deuterium gas that's boiling off of this electrode, pump it back around into a fuel cell anode so that you have oxidation of deuterium back to water on this side. So that reacts, the energy that it takes to do that, you're not really accomplishing any work here. So the energy it takes to do that at a conservative estimate would only be about a half a volt. So that's a very efficient process and requires very little energy to do. And the last couple of points I wanted to make, just one further thing about the actual pressures obtained in the machine. As most of you know, the confinement parameter, which is on the order of 10 to the 14th, 10 to the 13th, 10 to the 14th, I think a few parts 10 to the 14th to attain ignition in a plasma device, a high temperature plasma device. So we know what that is. We, of course, have extremely high temperatures in those reactions. In our case, we tried to form a simpler or a similar diagram, and we note from the lifetimes of the hydrogen in a palladium lattice and the density that we have in, we attain a very large confinement parameter or Lawson parameter on the order of 10 to the 36th. Even though we have our temperatures, of course, are a few orders of magnitude less than in the other experiments, it certainly means that we have a confinement parameter. So from the energy outputs that we get for the reaction we mentioned just a minute ago, these are the various rods we have used. These experiments now are essentially completed, and the open circles were experiments that were underway at the time. But these are operating in what we think is the break-even region for this given reaction. Of course, the other curve, this break-even line would shift up and down depending on which of the other reactions that you were attaining. But we're pretty sure that this is the reaction that's going on in the solution, at least at the electrode surface. This is the results for the sheet electrode, and this is the result for the cube that we had previously. Well, that's all the data I had. If you mind, can you put those overheads on? In closing, I would like to acknowledge Martin Fleischman, my associate in this project and graduate student who did most of the work in the recent months, Marvin Hawkins, Jerry Smith, who's in the audience, who has known about this experiment for some years and has always given us constant encouragement, Bob Hoffman for measuring the gamma ray spectra, Jim Brophy, Vice President of Research at the university, Ron Bullough and David Williams from Harwell, who have assisted us with some experiments towards the end of the work. And the last slide is acknowledgement of support. Sorry about that, but most of this work, well, all the work initially was funded by ourselves for some time, more recently the University of Utah and University of Southampton. And we thank Johnson and Matthew for supplying the rods recently or the rods for the experiments on their university loan program, and more recently for the Office of Naval Research for continuing support. Thank you very much again.
Are there questions?
Would you please comment on a report I heard this morning where you were talking with newsmen about the duplication of the experiment with non-deuterated water, regular pure water?
Chevis Walling and Jack Simons have presented a very nice theoretical paper to a journal, which they expect to be accepted today or tomorrow, according to the reports. And in this theory, they very accurately predict the fusion rates, the energies that we should be seeing. And a couple of the other predictions they made is that we should see, one of them was that we should see helium-4. And then we never looked for helium-4, and we went back to the old mass spectral data for January, and sure enough, there's two very well-defined peaks at mass 4, one for the deuterium and one for helium-4, which we've substantiated. We've gone back to the lab last Thursday and Friday and indeed have seen a large amount of helium, about 10 to the 4th times less than you would expect. I mean, 10 to the 4th times less than the D2 that's present, which is exactly the ratio that they predicted. A further thing they predicted was that the rate of reaction between deuterium and or between between protons and deuterons is about almost 100,000 times faster than the deuteron-deuteron reaction in their scheme. They have a scheme of of shielding by a heavy electron of effective mass 10 times the normal electron in that lattice. And we had tried, did not do anything quantitative on it, but we did try in January to get a blank experiment with a palladium electrode that we knew worked in regular water, and we did not get heat in, heat out balance like we had expected. We did get some excess heat. So that is still open for investigation. We are that experiment is set up and running again right now. But the heats were fairly small. The baseline experiment that we've done the most with has been a dead palladium rod, one that never got started because of some metallurgical reasons probably, or some surface effects. And that rod gives absolute, in the same cells, under all the same conditions, gives absolutely the same amount of heat out that you put in. But the active palladium rod that had been acting in D2O does not give that in plain water. It gives a slightly higher amount of heat out.
What data or scientific arguments makes you exclude the possibility that the additional energy you see is from other exothermic chemical reactions?
The amount of heat that's generated, I do not think can be explained by any known chemical reaction. You measure the volume of water that you're consuming. You measure the deuterium and hydrogen the deuterium and oxygen that you're getting out. I can't conceive of any other chemical reaction. All of the electrical energy that go after gases are evolved at the electrodes. If you measure the gases, if you measure those gases, that you could count for like 99.7% of all the liquid that's being consumed and all the gases that are being produced. So it balances. So I don't know what other chemical reaction could be sustained for that sort of periods of time that would give up that much energy.
I heard some discussion that the lithium as the electrolyte was not simply an alkali, but not probably replacing the sodium or potassium. Is there anything to this?
No, we are indeed doing potassium, sodium, and per-deuterated tetraalkyl ammonium salts right now. Lithium was chosen for a number of reasons, but we simply stuck with it during the whole tenure of these experiments. But lithium might play a part. It is plated onto or alloys with and is stable with in aqueous solutions on a palladium surface. So it is in the metal, but not to a great extent. But there is some in the metal. It doesn't diffuse very far in.
Would you suggest any difference between lithium-6 or lithium-7 on this?
I had one slide here. That reaction certainly has been implicated, and we will have to look for the appropriate products for that reaction as well. I think the sodium and potassium experiments will sort that out quickly. They do not alloy with palladium.
If you assume that all of your heat comes from conventional nuclear reactions, how many neutrons would you have expected? How much tritium would you have expected? And how does that compare with what you measured?
There's 10 to the 9th times more than we're seeing. We would expect to see 10 to the 9th times more than we can account for by the heat that we see.
So you say you can't understand how you would have gotten the energy by conventional chemical means, but we can also understand how you would get it by conventional nuclear means. Is that fair?
Conventional nuclear means, that's correct. The reaction that's been proposed is the internal conversion of an excited state helium-4 atom down to its ground state in the metal lattice. Yes.
Would you just discuss a little bit the ratio of deuterium to the palladium that you are getting in the deuteride, and also closest approach that you expect that you need to have in order for this to
We think from several considerations that we must be close to 1 atom of deuterium per atom of palladium in the metal. In conventional beta palladium hydride, you have between 0.65 and 0.75. That's after you take it out and measure it. But we think under the conditions of the experiment that probably approaches 1. And further, we think that these deuterons are located in the octahedral sites, probably multiple accumulation in the octahedral lattice sites in the metal. Hence the close proximity. And if there is an effective mass, large mass electron shielding these at this proximity, then it could be a cold fusion reaction.
At compositions of 0.6 to 0.7 hydrogen in palladium, hydrogen dissolved in palladium metal, and hydrogen in palladium hydride have the same, or essentially the same 0 point energy. What sort of transformation occurs at these higher compositions? How would you explain the disappearance of 0 point energy, which gives you the large separation factor?
Well,
At compositions of 0.6 or 0.7 hydrogen to metal or hydrogen to palladium ratios at room temperature, one has the same 0 point energy or within 10% hydrogen in palladium hydride as hydrogen in palladium. And the same is true for deuterium. Now, at the composition he observes, he sees the 0 point energy go to 0, which is just what you need, although 0 point energy gives you a high separation factor. How do you explain the disappearance of the 0 point energy? That is that at room temperature under normal pressures, palladium hydride is there as a normal quantum mechanical oscillator with an Einstein temperature of about 800 degrees Kelvin. Under his conditions, he sees the 0 point energy disappear, therefore the hydrogen is no longer localized within a site. Basically.
yeah, I mean, the only way we're going to tell is to certainly do ab initio calculations on this, taking into consideration the very high electrode potential across the interface. Go ahead. And, yeah. Okay. And under these conditions, I mean, it's simply that is what is observed. You do not observe these high potential differences if there's not an electrode potential applied. But palladium diffusion tube experiments, super base formation on the inside of palladium diffusion tubes, things like this certainly support that the chemical potential has been raised markedly in that lattice. So I think it is just due to the additional compression that is afforded by the continued diffusion of this material under the very high electrical potential conditions that you put on the surface, very high surface coverage conditions. So we're not going to be able to tell that until the proper calculations are done.
A second question. How does the metallurgical treatment of the palladium influence this?
All of our samples were cast. I think most of the commercial samples of wires that you buy are extruded. In one casting that did not work, this blank electrode that I told you that does not work, that particular one came out of the casting in quite bad shape, and they milled it, they machined it, and that one never worked either. So there is we think there is a metallurgical problem here. Certainly cast electrodes have a better performance ratio than extruded. So I do not know enough about that problem yet. We've sent some of the samples back to Johnson and Matthey for surface and bulk analysis.
Way back. And yes, and please speak up so we can all hear.
We've heard that the reads in your experiment on the palladium electrode have some role in results that you see. Could you elaborate on that? Do you need palladium reads on the palladium electrode, or
we have simply always used, in order to omit any confusion about junction potentials and other chemical effects that may take place, have simply always used 100 micron, I think it's 150 or 100 micron palladium wire that has been spot welded to the top of the palladium rod. That's always been our connection. I understand that there has been some extremely high junction or capacitance is measured between beta palladium hydride and things like copper, for instance. In fact, they exceed those of barium tantalate in some cases. So there is an implication that this leads to a much higher dielectric constant in beta palladium hydride, which can be seen. So I don't know. We need to look at that, but we've always just used the palladium. It seems a lot less ambiguous.
I believe you have made a comment that it's necessary to use palladium rods rather than, say, palladium foil.
Well, no, the reason we went to rods was to have a convenient method for maximizing the volume to surface area ratio, so we could unambiguously say that this process is a function of the volume of the metal. In other words, it takes place inside the metal. We have used sheets. Sheets, indeed, will be a method for building a conventional or a device, for instance, for heat production. But you can certainly use any geometry you want.
The important parameter is
you have volume. Well, no, the important parameter is that you have volume, period, so that you have volume to carry on the reaction. We just wanted to show that the effects we were seeing were not due to a surface chemical reaction. We wanted to show that it was a function of the volume. The important parameter is volume.
But if you reversed it and used and didn't control surface area, just controlled volume, you'd expect the same result.
I don't follow that.
You said that only volume was important.
No, we simply wanted to show that the heat, the excess heat we were seeing, was a function of the volume of the electrode and not the surface area. I mean, as you make the rod larger and larger, if you make the rod larger and larger, we have a direct relationship between the heat involved and the volume of the electrode. The area increases much slower, at a much slower rate, and so we did not. So it's.
Well, you can show that by maximizing the volume to surface area ratio, or
Well, that's what you do with
you
it.
can show that it's independent.
Yeah, I mean, a rod is simply the most convenient way of doing that. Because you have, I mean, you could go to spheres. Spheres would be ideal, but that's very difficult to make. So rods give you a very high volume to area ratio, so you get a lot of the effect. Number one, and it brings it away from the surface area dependence.
In the experiment which detected helium, what was the idea?
Can you please stand up and speak loudly so we can all hear?
In the experiment which detected helium, what was the ratio of helium 3 to 4?
Helium 3 to 4. We have not measured helium 3. I think its mass is too close to. Is it? I don't remember if it's tritium or the H3 plus that it's so close to. Both which are present in the system.
I understand that D2O can have tritium in it as an impurity quite often.
That's correct.
Is there any tritium in your original?
Yeah, I don't have a copy of the paper with me, but it's in the paper, and that's the experiment which I showed here started out at 18 disintegrations per minute and ended up at 100 and I just don't remember the figure. It's something 225, something like that per minute. It's in the paper, and it goes along a curve which was predicted by the differential equation which we solved for the accumulation.
Do you think the peculiar properties of palladium are essential to this experiment?
No, I think any number of metals which show high, or alloys which show high hydrogen permeability may be of that crystal structure anyway, could give the same result. We have not tried any other metals yet, but we certainly are going to try titanium, for instance. titanium absorbs many times more hydrogen at high temperature than does palladium.
Do you have any comparison between the amount of helium-4 that was measured in the earlier experiment and the amount of excess heat?
Again, that prediction is in the Simons-Walling paper. I'm sending copies of that down to Rulon in the next few days, so he will have that and make it available to you. But they made a very close prediction as to the excess heat generated.
Have you tried to pre-saturate your palladium with deuterium to change the initiation time of the reaction?
No, that's something that needs to be done. One thing we want to start doing is trying to load them at higher temperatures, say at 80 or 90 degrees, and then cooling them down for the experiments. But there's a lot of ways probably to do that, and that needs to be done.
What evidence do you have that these lattice sites are multiply occupied?
We have no direct evidence that they're multiply occupied.
Calculation?
We are doing those now. Jack Simons is doing some ab initio calculations on those now.
Can you describe how long after the initiation of the experiment you first see excess heat, and then subsequently how long does it take the excess heat to reach equilibrium?
All of the experiments are at equilibrium, well, up to a 4 millimeter rod are at equilibrium by 250 hours after we start. There is a slow rise, well, there's the expected rise in temperature that you would expect from just joule heating in the cell over about several hours after you start the experiment. And then for an electrode that takes, say, 3 weeks to charge up, you will see not too much of a change over the next week and a half, and then in the last week you will start to see the temperature rise from that up to the 6.5 degrees that you saw here. So that temperature cycle takes about a week. We usually wait about 5 times the diffusional relaxation time before we think the thing is at total equilibrium.
Can you describe a little more about the experiment that failed and what you observed when that was concluded and what you did to analyze the results and what you think?
Which experiment is that now? The
one that vaporized or self-destructed?
It was a bit of a mess, to say the least, but that had been running for several months, and we decided to start doing the thermochemistry, so we wanted to turn the cell off. So we turned it off too quickly, and several hours later that accident happened, and it vaporized 90% of the cube and the bottom of the vessel and some of the surrounding materials and equipment in the hood. That was also a cast, by the way.
How do you derive the confinement parameter 10 to the 36 particles per cube?
We've simply taken the estimated lifetimes of beta palladium hydride that are in all the metallurgical texts, and assuming a density that we would obtain by having one hydrogen atom per palladium atom in a volume that size, and multiplying them times each other.
The plot of the contained velocity criterion that you presented showed a horizontal line of break even. Is the scaling of that just simply based on the observations you had apparent break even?
Yes.
Or it's not a theoretical?
No, no. That comes from the calculations in the first table.
Is there a short-term correlation between the current flow and the heat reduction rate?
Short-term?
Yeah, what's the time constant for changes in heat rate if you change the current?
Well, the thermal relaxation time of the dewars we've been using are on the order of, I think, 1,800 seconds. So any change, you would have to wait that long before you could determine what the cooling constant, the new cooling constant was. So the measurements are simply slow. Apparently it goes up, at least within that time frame, within hours. I mean, we could do that for large electrodes. We could do that experiment in a test tube instead of a dewar, so that we would have a much quicker cell cooling constant, or much more rapid attainment of equilibrium, and make those measurements. And we are going to do that with the larger electrodes. We don't have to have such accuracy with high heat.
Suppose everything works great the way you think and hope that it does. What do you see as the critical things that would need to be done between here and getting practical power output?
Well, just getting a database and find out what these electrodes act like is a function of geometry and everything as you scale them up. We have to scale it up and see. It's going to be I don't see any problem, but we just need to see what the radiation looks like and what the thermal balances are as you start to make the devices larger.
You mentioned that there's a possibility of the nuclear excited state of helium-4, which, if I recall correctly, has about 24 MeV of energy over the ground state. Do you have any mechanism how this may be given up? Is it going to be given up as gamma, or do you think?
They think the energy is dissipated to the massive electron that's binding them, that's shielding them.
Do you think it could yield phonons in the lattice and not a bunch of gammas?
That's clearly a possibility. Because of the dielectric constant measurements that have been made, there is good evidence for a larger mass electron. So I think when the paper comes down, take a look and see. They make a pretty convincing argument.
Have you looked for X-rays?
No. It's a good point.
And likewise, have you found any evidence of higher energy gammas?
No, we've looked for 22 MeV gammas and have not seen them.
Do you have any data or can you postulate what the effects of highly elevated or depressed temperatures would be of the reaction?
Only that on this last electrode that we have used, which is a 4 millimeter diameter that had been clipped down so we could get higher current densities, the temperature changes then are quite sudden and are quite spectacular. It goes to a certain level, hangs there for 2 or 3 days, and then makes a sudden jump of several degrees, not just tenths of a degree or hundredths of a degree, but several degrees. And it did this 3 subsequent times over about an 8-day period, and finally evaporated all the water out and open circuited. So we've now started that. That happened about 3 weeks ago. We've now started that cell back up. So obviously at higher temperatures there are some erratic effects which we don't understand yet.
You mentioned the possibility of clusters of neurons in your March.
Again, this just gets you back to the multiple site occupancy of deuterium in the lattice.
One furthest back.
Can you exclude the possibility of fusions being initiated by adventitious radiation?
No, we cannot.
If the tritium and neutron production is down by a factor of 10 to the 9, is the crucial issue to demonstrate a nuclear reaction the quantitative production of helium-4 consistent with the amount of heat that you see? You feel that's the crucial measurement?
I think that's a crucial measurement, yeah.
Have you examined your palladium electrodes after the fact to see if there is any metallurgical change? We always believe
The state of beta palladium hydride is extremely hard, very hard substance compared to the soft raw palladium. But in these cases, when we finish with a rod like a 4 millimeter rod, the additional intercalation of lithium into the lattice makes it extremely hard, and it will totally destroy a brand new hacksaw blade if you try to cut it. We had to use about 2 blades and take about 15 minutes to cut a 4 millimeter rod. So it's an extremely hard substance, and so there definitely is surface metallurgical changes, at least with lithium present.
Why should turning off the current from the cell quickly lead to very large reduction of energy?
It leads to large and steeper concentration gradients. Agreed, it's moving in the other direction, but there is a sudden concentration gradient developed in the lattice whenever you change the...
Why does it lead to a sudden concentration gradient?
Because that will lead to higher compression. Because why does it...
Yeah, have you done a calculation that says...
Well, you have a steady state concentration gradient.
Yeah.
And when you change
turn it off quickly.
when you change one of the boundary conditions sharply, then there will be a sharpening of the concentration gradient.
Well, if you think that this is an important effect, which you obviously do, why don't you try to control for that? That is, get larger effects, but not catastrophic.
We have done some potential step experiments, but again, these things must occur over long times. And in one experiment, we saw increased rates of neutron production on a 1 millimeter rod when we pulsed the current quite drastically over some periods of time.
To your knowledge, has anybody seen these large excess heats 10 to the 9 times larger than conventional nuclear reactions that they do?
With regard to the excess heat, given the long duration of the experiments, have you integrated the total electrical energy input and compared that to the total thermal energy output for the entire duration of the experiment? Is that really?
Yes, the one we reported in the paper, we reported 4 megajoules total integrated energy, and more recently we've obtained 50 megajoules on the 4 millimeter rod for 800 hours.
The question had to do with the ratio of the electrical.
That's the excess energy. That's the excess energy.
Are your measurements consistent of neutrons and tritium production consistent with equal branching ratio for
the amounts of helium, the amounts of tritium and the neutrons measured were approximately the same.
Do you think you've accounted for all the tritium? Is there some tritium trapped still in the palladium you're not measuring?
Well, we're making steady state measurements outside, so we assume the neutrons would come out. But the steady state tritium in the literature, in the electrolyte is what we measure from the equations. I mean, we know what that concentration is, we know what the separation factor is, and we know what concentration that must lead to over what period of time. So from that we can deduce the absolute amount that has been generated. It's pretty consistent.
When you say that the excess energy is 4 megajoules, what's the total energy?
That's the total energy would be that plus.
What is the comparable number?
Oh, I'd have to calculate it. I mean, you would.
20 megajoules? We're talking about small differences between large numbers,
Well, it would be the voltage times the current. I mean, the voltage minus the 1.54 times the current. All of that multiplied by the total time of the experiment.
But is that number comparable or very much larger than
that number would be in the typical experiment would be larger, about probably a factor of 2 in the typical experiment.
So the excess energy is approximately twice the total energy.
Well, they were present in the percentages in that table. They're of the total energy. Yeah, the total energy would be the one with the twin stars in that table too.
It was in your second table.
It's in the second table. So they're on the order of 10 to 50, 60%, something like that.
I mean, the table in the paper was calculated, it had 3 different reactions, and one was an excess over joule heating.
Right.
And I believe only 1 out of the 9 entries had a number greater than 100%.
That was the 4 millimeter rod, the last 4 millimeter rod, and 111%.
So doesn't that say that the differences over the joule heating alone are small? Or? I mean, I may have misunderstood, but I thought there was only 1 entry in that table which had an excess above 100% of the joule heating.
That's correct. It was 111% 4 millimeter rod. That has now been exceeded quite quite a lot by this other 4mm rod running at a half an amp per square centimeter. But in that table, that's correct.
I hope that you'll join me in thanking Dr. Pons